Welcome to part 3. In this part, polynomial models are explained. Let's look again at the blood pressure data. We have 6 data points, and the independent variables are the x values, are the years 2014 through 2019. The dependent variables are the pressures, the systolic blood pressures. These are indicated with the variable t. Think of t as the target value, the value we're trying to predict. The variable y will be used shortly for model functions. Note that the data have units, time for the years and pressure in millimeter mercury. Soon these units will be dropped. Data are rarely coming without background knowledge. And for blood pressure, there is a lot of background knowledge. Blood pressure depends on gender, age, weight, and a couple of other factors. And from that background knowledge, we can tell that the pressure values look reasonable. On the other hand, there is no physical law which predicts blood pressure as a function of time. So we need probabilistic methods. Also, we have only 6 data points, just enough to show all the details of Bayesian regression. Actually, these are real data, and the advantage of real data is that we don't know the truth of an underlying assumed model. And in this way, we get confidence in ourselves. Polynomial models are often the first aid kit of data practitioners. But beware, they are an arbitrary choice and alternative models could be better. I assume you know what polynomial models are, and in fact the notation I employ with A's and B's and C's is not very handy. It is much better to use W for the coefficients. So we write the polynomials with W and subscript. The sum of the polynomial model expression always starts with 0, and the number of terms in the expression is always 1 more than the degree of the polynomial. So for the polynomial of degree m, you have m plus 1 coefficients. Well, let's just first have a look at the least squares models, just to get acquainted. Here we have a constant model, but we are in a different state of knowledge as in the boiling water example. We know that blood pressure is allowed to vary. Therefore, a constant model is rather restrictive. Here's a linear model. It's perhaps not too bad in the short term, and note the predicted value for 2020. Here's a quadratic polynomial or a parabola. And one of the things you can notice is that the fit is reasonable, but the extrapolation goes outside of the range of the data. That is perhaps not a problem, but it's something to be noted. Here is a third-degree polynomial. Actually, the fit is getting closer and closer. And the prediction is not too great. A fourth-degree polynomial, this is really a good fit, but the extrapolation is really very bad. It's it's beyond the scale of the figure. And here is a fifth-degree polynomial, and that's a very good fit, And the prediction is actually not too bad. So what do we need? We actually need a way to select models. And selecting models is the unique selling point of Bayesian regression. But where is Bayes' theorem? Well, you have to be patient a little longer. In the next part, we are looking in more detail at the misfit and the residuals of the model and the data, and we will define the error function, which forms the basis for the least square solutions which we have just seen. See you there.